Afternoon to all. Now we will continue with the first topic on the advanced process control. Myself, Muhammad Hussain, Mr. Mraya. And basically, today we'll be talking on the first aspect of the advanced control, which is the advanced conventional control strategies, which we have mentioned before. In the advanced control, we have two different categories, the conventional and the modern control strategies. And this is some of the conventional ones that we normally use, the cascade and the ratio control, which is in the normal process control books. They also have this under advanced control, but normally it is still related to the normal conventional process control strategies because it's just a slight extension from that. But still, it is still under advanced control because from the definition we've given before, anything different from the PID or from the PID control loop strategy, we call it advanced control. Although it be conventional or modern, it's still under advanced control because of the difference between the advanced conventional and advanced modern control strategies. So among those in this conventional, advanced conventional control strategies are the cascade and the ratio control strategies, which I will be going into first on the cascade and the ratio control. And as you will see, there is not much difference from the PID. The PID control is the PID, but the loops are different. Now we have more loops, right? Okay. In this example, if you can see, we have the normal conventional control method, and then we have the cascade control strategies. In the normal conventional control strategy, if you want to control the temperature of this reactor, CSTR, jacketed reactor, so normally we will be manipulating the coolant flow rate into the jacket, coolant flow rate. Okay, so if we have the set point for the temperature of the product or the reactor, okay, the inside and outside is the same. So basically we will be measuring that, and the set point is basically is going to be the set point for the coolant flow. So although this is measured, and but the set point is actually the coolant flow that is being sent through here. All right, so we can see that the effect is actually controlling the temperature but manipulating the coolant flow. So there will be an effect at the end of the day because the coolant is around here. This is exothermic system, that's why you have coolant. Okay, if you have endothermic, you'll have steam. So it's having the coolant here. So basically, it's trying to control the coolant flow. But we can see there will be slight delay here. Yeah, because of the effect of flow on the temperature will be not a direct effect, indirect effect. So there will be some time before this one is affected by the coolant. And also if there's changes here, the temperature here will also be changing all the time. So this is okay. This strategy is being used, commonly used, but there's some problems to it, as I mentioned just now, and things like that. Especially if you have the coolant flow changing, then it's going to be always changing, and we will not get a steady state control easily. So this is why what has been proposed is to have sort of a cascade control strategy. Yeah, you can see the difference here between the conventional and the cascade is that you have the same loop here, but you also measure the temperature of the coolant inside the jacket, because it may change. So by measuring it, we also have basically two measurements coming in. One is a measurement of the temperature, and that is the set point we want for this one. This is our set point, but at the same time, this output from this first controller is sent to the second controller, which is basically controlling the temperature inside the jacket. So we have a loop inside the loop, and this anyway will be manipulating the coolant flow, which is the standard manipulated variable here. So this is the cascade control, right? It's not the normal. This is the normal conventional feedback loop. but this is the cascade control because we have two loops inside a loop. As you will see, when we start to draw the block diagram, we'll see that this is another loop inside the loop, and you have basically two set point. One you set yourself, one is inside the system itself. In the cascade control system, that is the set point for the what we call this the secondary loop, and this is called the primary loop. The system is the same, the manipulator is the same, measurement is the temperature, also another measurement for the jacket which is also been measured. So for the cascade control, basically what we have is two measured variables just now we can see, and one manipulated to measure the temperature of the vector and the temperature of the coolant, and the manipulated is the flow of the coolant. So basically we can say that the CSTR, the outer, basically the outer loop is the primary loop which measures temperature and use that set point from the operator. You decide the temperature of the vector because that's the main primary loop, that's the main temperature you want to control. And inside there we also have the secondary loop, yeah, which measures the coolant temperature, okay, and use the set point from the primary controller, and that these two loops make this what we call cascade control. Okay, so cascade control, we have the primary loop controlling the outside temperature, and we have the inner loop, secondary loop controlling the temperature of the coolant. And because you have two loops, the loop is not the normal conventional, so this comes under the advanced control strategies, methods, and but it's because it's a slight improvement over the normal conventional method, so we will just call it the conventional advanced control, but in the conventional type, the basic normal type, which has a slight extension over the existing one. So if we talk about the loop again, see the loop again. Okay, this is the open loop process of the system. But if we look overall again, we can see that this is the conventional feedback loop. Okay, we have the controller for the flow, okay, the flow system, flow the manipulated loop, we call it process 2, and this is the process 1, which is the reactor itself. So in trying to control the temperature of the reactor, which is the output here, and measuring here, and set point from your outside the primary one, we have the controller that is manipulating the flow of the coolant, and that controls the process. So we have a problem here, as I said, we've seen mentioned before, because process 2, the coolant part of the process can change, can be changing, and we don't have control over it. So by using the cascade control method, so we'll have the same thing outside, but also inside the loop we measure the temperature of that coolant, and then we check with the set point coming from the primary controller, then it was used to drive the secondary controller to control the flow of the coolant. Then that will become the basic output to the change the process 1 is the temperature of the reactor, and this is temperature of the inner loop, the coolant loop. But at least when having this, we have the inner loop, we call the secondary loop, to control any changes inside the flow of the coolant. Okay, the change of coolant flow definitely change the coolant temperature, things like that. It may affect, so we control that part, so that it is not too much variable here, and then only we control the temperature of the process 1. So what we can see here is that two measuring device and two measuring device and two control compared from the normal process, normal conventional feedback. We have one controller, one measuring device. It's a normal, but here we have two loops, and we have two measuring device and two controllers. But the manipulated is only one, same manipulated. There's no two manipulated. There's two manipulated. We have a different memo system, but this is still a single output system. So the manipulated is still only one. The manipulated is controlling the flow of the coolant, so it's only one. But we have the extra controllers and the measuring device. So we can see here what's happening is that the set point is being given by you, the temperature of the controller, so the temperature of the vector set by the primary controller, and then it is used to drive a set point here for the secondary controller, which is also normally the conventional controller, to drive the flow of the coolant inside the secondary loop. Here the disturbance are all standard. So these are normally anyway. The normal conventional can be PI, PID. We'll see normal. We'll see later that is normally the PI or PID. This one can be PI or can be also the P controller. And also we have the open loop transfer function and characteristic equation of the two loops. We look at the secondary loop. We have the open loop transfer function GC2 GP2 and the characteristic equation given by 1 plus GC2 GP2. This determines the stability of the secondary loop. As normally we do for stability check, for even for tuning, we can use this for the secondary loop. And once we have that for secondary loop, we combine with the outer loop. We got the controller for the primary loop plus the closed loop for this secondary loop given by this, and the process of the primary loop, which is the reactor itself, the CSTR itself. So the characteristic equation is just 1 plus this open loop transfer function again, 1 plus this is a normal characteristic equation again that will be used to design our controller, the stability of our controller. The tuning also can be done using this to make sure the whole control system that we have for this cascade system is stable and can be used for the system that we have in particular. And some notes is that for the secondary loop, in the loop P or PI controllers are used normally, but for the P primary loop, normally we utilize the more what you can say, the more sophisticated or more much better PID controller. Okay, so we know the P controller we have offset. PIs normally we remove offset, but we can have instability problem for PIs. But the PID is normally more stable and reduce the offset altogether. Normally that's the best, but of course you can see the problem here. You got 3 tuning parameters, you got only 2, and you got 1. Okay, why is that we can use P? P controller have an offset. Because the main fact is that because the secondary controller is not our main loop. The secondary loop is not our main loop. So if the slight offset in that small offset in the flow and all that, that doesn't really matter. The most important is that there's no offset in the outer loop, which normally we use PID to make sure that it's no offset and so on. Because the main purpose of secondary is just to cater for any changes that can come inside that secondary loop. And so once we have a loop, at least control loop, at least we can handle those small changes in the secondary loop, and at least so we can variables and the disturbance can be handled slightly, and then only the primary loop takes over to control everything, make sure it's as perfect control as possible without any offset. And the secondary loop dynamics has to be faster than primary loop. Okay, it's quite obvious because we have to operate the secondary loop first before we operate the primary loop. So it has to be faster dynamics. It means the measurement has to be faster than the primary loop. Can be the same what you call dynamics, time constant, same speed of dynamic speed, but should not be slower. So it has to be faster. It has to handle the control secondary loop faster, the change in the coolant faster than the primary loop. So that is important. And normally it's the flow. Secondary is normally flow, can also be if both temperature is okay, but normally it has to be flow. The outer loop is a longer one, temperature constant. This issue of cascade normally for slow systems. So the primary loop is normally the slow system, but secondary loop is always the faster system. This is why normally the flow is being used to control the secondary loop. And normally what we do is that we tune secondary loop first before the primary loop. It's quite obvious because secondary is inside. We have to handle that first, so we tune that first, okay, by manually or trial and error, and then only we go to the primary loop, which we have to do more sophisticated tuning. The tuning of the outer, the primary loop is most important. Like supposed to say, primary loop is the main loop. It's the one that we are trying to control. So we have to give more time and attention to the primary loop, and so normally you can do it well if your secondary loop has been handled. But it takes more time because as you said, the primary loop normally consists of the PID controller. So it takes more time to be able to tune that primary loop as compared to tuning the secondary controller. So, okay, so the normal procedure that we will use to do that, and you can see examples of Cascade. So many. Yeah, the industry, there's so many examples in the real world. There's so many examples of Cascade. In this one, we have a Cascade loop here. The main thing is to control the temperature of the heat exchanger here, coming out temperature. So we have this primary loop, but at the same time, we want to also take care of changes in the stream one. So we have a secondary loop to control the changes. So this secondary loop, this is a primary loop. Okay, the two controllers, temperature controller, flow controller, and the two measurement, temperature and flow. And the main loop is the primary controller, and this is normally the PID controller. As I said before, this can be the P or the PI controller. Okay, for flow, of course, normally we use the PI. P can be which is side offset, doesn't matter, or PI for the flow. PID normally we don't use for flow anyway. And the other one is the for your decision column. We're trying to control the temperature of the, in this case we are controlling the temperature of the top trays. Okay, temperature control. At the same time we also manipulate the secondary loop, the flow, the reflux. Okay, because the reflux has a straight effect on the temperature, but the reflux can also have some difference based on the sort of connection you have here, can be changing. So you control the reflux to the secondary controller, then you control the temperature to the primary controller, and set up what we have the cascade control loop for the top temperature control of the station column. That's the top. Bottom also, we want to control the bottom of the trays. Is affected by the reboiler steam. So we have the primary controller for the temperature of the tray, but the steam can change. So we do a secondary controller loop on the steam flow inside this inside here. So the FC for the steam is the secondary controller. The TC for the temperature is the primary controller in the reboiler system. So it's an effect. Whatever changes here can handle it much better. With of course more tuning being done here, because we have here need a PID and here we need a P or PI. So two tuning. Well, as I said, this is a quick one, a manual one, and this is a more rigorous and more important, accurate tuning to be done for the primary controller. And then we have another example for a sort of a boiler system, boiler system. So we have fuel coming in, we want to control the temperature coming to heat the stream. Okay, so we have this the main primary control, primary loop, primary controller, but we have changes in the fuel, so we need to handle that. So it is done by secondary controller, and the FC for the secondary controller, and this TC for the primary control. This is the main loop, control the temperature, but the variation in the flow is taken care by the secondary controller for the fuel. So these are some examples. There are many examples in Cascade which we can use. Okay, some of them, not all, necessary to have Cascade. If you can handle by the conventional, small different loop, minor loops, you can use the normal conventional, but loops are major to control temperature of the station column and heat exchanger, which are major loop. The Cascade should be able to give you better results than the normal conventional method that we always use in our previous work or previous class that we've been studying on process control basic. So if you have a set point problem, then okay, just simplify this cascade. We can simplify in this block diagram here. Okay, as we've seen before, the closed loop transfer function is given by this one. Okay, for set point, we should see over the R. Yeah, so we can get this for the set point problem in the cascade system. These are some example of the sort of response that we can get using conventional and cascade. For example, we have a set point change for that sort of system. Okay, for conventional, you will see that it's a bit slower, more oscillation, but for cascade, faster response, smaller overshoot, and quickly go to the offset. Okay, for conventional, so we show the KC 2.84 and TI equals 5. For cascade, we have two controllers. Yeah, the primary controller, and we're using the PI for the primary controller, so TI 0.63. And for secondary, as you say, we can use the proportional controller only for the secondary loop, in this case KC equals to 10. And of course, different tuning parameters for the conventional PI cascade, but you can see the result is quite different. Okay, the cascade is much better, goes quickly to the set point, less oscillation, less offset, less overshoot, offset. Both of them are the same actually. The end is the same, but this takes longer time to reach its final destination. So although it achieves what we want, but it takes a longer time, and sometimes we cannot afford to wait. So cascade, you can say, it goes quite much faster than this normal conventional in this system. But in most systems, in general, this may be sort of result that you will get when you're dealing with normal process control system for using cascade and conventional methods itself. And you have a load change problem, which is actually the disturbance problem. Then if we have the system, we want to simplify to the final closed loop system. Okay, we do a little bit of block diagram and manipulation. We have studied in your block diagram manipulation. Handle this part. Okay, the process inside the secondary loop, this process outside in the secondary loop, the primary controller, the secondary controller. Okay, little bit of manipulation here and there because we want to get the C over R at the end of it, or C over U in this case, load change C over U. So we have to simplify. So a little bit of simplification within the loop itself. Okay, and then movement of U to the R, because we're saying this is just a load change. Just now was a set point and no disturbance, so U was 0 and change the set point. Here there's no change in set point. Not that set point is 0, but no change. This is deviation variable. Okay, so we're talking about no change in the set point value, and in this case the only change in the disturbance of the system. So if you modify further, then we will get this sort of loop. And what we're gonna get is the C over U is given in this form. Okay, so this is we can get the final C over U, the output over the disturbance that we need. Normally in control system, we always have to do the set point change. We call it the servo control, or the disturbance change, which is called the regulatory control. So we got the set point just now. Now we're going to do the regulatory control manipulation or analysis. So we get C over U, and then this is what we're going to get. If we simplify them, we get this sort of thing. And again, if you look at that, we can see the different response that we are going to get if we are going to use these two different controllers. If you don't do any control at all, of course, you will just, if there's any change in the disturbance, we just follow the disturbance change, and then there's no control. Okay, that's the problem. If you have no control at all, we'll be facing this sort of system, and the system will be unstable, will be offset, will have a lot of problems of control. Okay, if you use conventional PI control, okay, which is the case 2.84 and 5 was mentioned just now, so you'll get going some high overshoot and high oscillation before it goes back to the set point. The set point is there's no change in set point, it's only the disturbance that making it change. So with this change in disturbance, the output is also changing. Output is moving away from what it has been set for, set point. In this case, set point. We don't change the set point, keep it, but disturbance change it. So we have to bring it back to the set point. And in using the conventional one, you can see a lot of oscillation and a lot of overshoot. But if you use the cascade system, in this case, okay, then you have the KC changing for the primary controller and tau I primary controller 0.63, and the secondary controller KC constant as before. Then we can see that there are very little, very little overshoot and very little oscillation. Very little overshoot and very little oscillation goes to the set point faster than if we have just the conventional method itself. So this is the advantage of having this sort of cascade control system that's definitely makes the response go faster back to the set point or to the new set point that we want for servo control just now, and also cuts down on the oscillation, which is very important when you have systems like we see just now for the distillate control, temperature, coffee boiler control, and for heat temperature control. We need it to go back quickly to the set point. Cannot afford big, like long time. We cannot afford too high overshoot, which may go beyond some specification of the distillation column or the heat exchanger. So we need very tight control, and only this cascade can bring it back very fast to the control action that we want, and this is more suitable for our course of action in this case. It shows again the advantage of cascade control. Although we have more tuning to do, but it's got a lot of advantage, and it's only the main tuning is also just like this one. The conventional, so the main tuning is the primary, is the main one loop. They have here we have two loop, but this one is the main tuning. This one will have another loop, but the tuning is just simple tuning. Try and have a speed controller. We don't need too much refine, because at the end of the day, we want to control the primary loop or control the temperature. Temperature is given by this part here. That's the main aim. So this has to take more time. This one is much simpler and easier. Okay, so the second type of controller that we have under advanced conventional is what we call ratio control. Right? It's nothing so difficult about this. What it means, ratio control, is that basically we want to have two variables at a certain ratio between them. So two variables measured and set at one ratio for any system. And for example, normal one is, we call it the ratio control that normally we do is for flow ratio control, which is quite common. Yeah, to have ratios between two flows, we can use this ratio control action, ratio control strategy, and again it's under the advanced convention. Although it's nothing much advanced, the controllers are still PID, but again, due to that definition we have defined in the introduction notes, yeah, as long as it's not within the normal conventional loop, okay, not using the normal conventional controllers, so you put them under advanced conventional advanced control. And normally what happens here, again, two streams are measured, but only one is being controlled, only one control. Okay, and the other stream that is not being controlled or not measured, we call it as the wild stream, the one that is just changing and moving. Because of that, normally the ratio will change. Because with one wild stream, the ratio keeps on changing. So that needs to be controlled, and that's why we have to have this ratio control to control it to the ratio that we want for the particular system. And this is a very typical example of a ratio control that is being used. And in this case, we are trying to control the ratio between this stream A and this, between this stream A and stream B, the ratio here. This is the controllable stream where you valve, the control manipulator is here. This is not control at all, so it's the wild stream. You can measure it, but you don't have a control action on it, so it's called a wild stream. It maybe you can control it, but not necessary, because what you want is a ratio, and we need to control only one. Okay, so in this case, we measure the control stream FB flow of control B, measure FT1. We have a divider to divide the ratio, and we put it into the controller, and then we compare with the desired ratio. Okay, how much it's close to the desired ratio, then we act on the controller. We call it a ratio controller. It acts on the valve, and then hopefully gives you the ratio that you want for your system. Okay, whatever ratio that you want between A and B is being executed here in this way. And this is one way of having the other alternative configuration that we can use for ratio control is basically to have we have the measurement. Both of them have the measurement. We still have the control stream control or flow FT2. We measure FT1 and we get the ratio. Okay, and then we get the ratio, and we get the flow here. We times by the desired ratio that you want, so that this will give you the FT2 that you want. You know FT2, you know FT1. You know the ratio that you want, FT2 over FT1, the desired ratio. So by calculating with the desired ratio, this should be the desired, basically FT2 that you want. And this is the actual FT2. This is desired. So this becomes the set point, and this becomes the actual measurement. And so you will just execute the ratio control, just execute on the valve based on just the change between desired flow and actual flow of FT2. So desired flow is not it's not being used to compute in the control action, but the desired flow is being used to compute the control action. And this is normally the one that is normally being used, because this is more stable than using the previous one that I have shown you. Yeah, why? Because this one doesn't have ratio. When just now we divide this by this, and we use that as the measurement and the desired ratio, the division can be quite unstable. If you have one of them, say low, it can go very high ratio, yeah, close to infinity, and you compute that in the system may be unstable, may not be able to handle. Okay, because you have one very low, one very high, and you divide a very high number, and that high number may not be able to be computed by the computer or by the system. Of course, it can do it, but it's not stable. Okay, one very high, maybe it's close to very close to zero, and this is say 1000 and divided by close to zero. You can imagine the number that may come out, and that's very difficult for the system to operate, or the controller to operate. So what happens normally, we prefer this system, because this is talking about just flow. This desired flow, actual flow. Normally the error is not so hectic or erratic, not so much instability in this sort of system, so it can still be handled. So this is more preferred way of executing a ratio control strategies in the real world. And you look at the block diagram for the ratio control, it's the same system here inside the loop, but it's the only thing now we have the other loop, which is we call the while loop. Yeah, so we have to measure it and calculate the desired ratio that we want, and get to set point for this flow FB. FB is the flow that we are manipulating, the flow back there where you have the valve. Okay, so that is the flow that we need to set at to achieve the desired ratio. You have a desired ratio between FB and FA. You measure the FA, this wild stream, this is not being controlled, not being manipulated. Yeah, it's changing all the time. So there's the wire stream. So you measure that time the ratio that you want, you get the set point of FB that you need to have, and compare with the actual FB measurement, okay, and get the controller which is ratio control, but a normal controller can be PI control flow, and then it goes into the valve and goes into the process and control the FB. Okay, control the FB flow. So you have disturbance. In this case, could be the pressure change. It could be disturbance for the system. Yeah, changing that is happening inside the FB loop. Could be the change of pressures and so on. So these are disturbance. And this is one means it's because what are doing? We are measuring flow and we are manipulating flow. So it's a flow-to-flow system. So the transfer function is just one: output flow, input flow. This is normal for flow control. But the transfer function is the one, which is the one-to-one change in the block diagram or in the transfer function. Why you call it advanced? Okay, this is not this typical conventional loop, but you have the extra loop here, extra part here. So they prefer to put it, and it's not really that advanced, but still it's something different from the rest that we have seen before on the conventional system. You have two measurements. Okay, you have two measurements here for FA and FB, so it's slightly different. Okay, and you're talking about ratio, not just the flow. And so there's like alternative it comes under some advanced, but conventional, very conventional system. The controller is still the conventional controller, like Cascade. The controllers are all still conventional. They are not advanced controllers. You don't need them also. You just need the conventional PI, PID, but just the slight loop, because based on the definition, again, look back at the definition, anything loop that is different or any controller different, either one is called advanced control. Okay, and in this case, for the Cascade and for the ratio, it's just that the loops are different slightly. So it comes under these advanced control strategies, be it in this case conventional advanced control strategies and so on. Just one tuning here, but still slightly different loop that makes it under advanced and for ratio control. Okay, again, as I said, just try that it's called advanced, but still under the conventional advanced method. And if you look at the control loop transfer function, you can relate the FB, which is the flow that you want to manipulate at the end of the day, to get this ratio, to get the ratio right. You manipulate FB, but the ratio is what you want, FB over FA. Relation to FB with respect to FA, okay, which is your wire stream, and PB, which is your disturbance, is given by this, the normal closed loop transfer function that you get from the normal loop. Okay, with the additional, of course, you have this desired ratio that comes in here, and you also have the GM1, the measuring transfer function that comes in here. And for this, you have the disturbance, the transfer function with respect to pressure here, that with respect to the flow. Okay, flow and temperature, pressure have got close relationship in terms of one another. So we can see that it's important to put transfer function. And the bottom part is just the closed loop, the characteristic equation, which is 1 plus open loop transfer function, 1 plus open loop transfer function. This is the characteristic equation that will determine the tuning of GC, determine the stability of the system here. Okay, it determines how it's going to behave, the mode of behavior, and so on, as we have seen before in the conventional studies you have seen before. It's the same, similar methods can be used here. The same method just for Cascade, the open primary loop, secondary loop, and for this visual control, the similar methods for tuning can be used. The clinicals or Cohen-Kuhn, whatever, is the same, because these are conventional controllers, so we use the same method. And similar methods of stability check, Rao's law, checking the roots of these can still be used, because they are still conventional controllers where we can use the conventional techniques to analyze stability, to tune the controller, to analyze how the system is going to respond with set point change and set point change. Okay, in this case FA. Set point change is here, but the change is also related to while stream. The while stream that change that makes you need this control loop. Okay, if there's no while stream, there's no need for this control loop, ratio control, because the while stream changing, the ratio change. So this has to set back whatever change the ratio changes. This is desired ratio, but whatever changes, this one has to set the set point properly, so the FB also change accordingly, so that the ratio is constant. The flow may be changing both sides, but the ratio is constant. And if the disturbance change and you have a disturbance system, you have a disturbance, so the disturbance will affect again the flow, will affect the pressure. So the pressure will affect the flow will affect the ratio. So again, you have to handle the set point and the disturbance. As I said before, any loops, whether it be conventional controller, whether it be advanced controller, we have to analyze from both sides. The set point change, we call it the servo control method, or we have to analyze based on disturbance change, which is called the regulatory control method. So all this has to be properly analyzed from both sides. And when we tune, we have to make sure the tuning is good enough for set point change and good enough for servo control and good enough for disturbance change, which is the regulatory control. Okay, that's why only we can say that the tuning is right. You cannot have just one good, the other one not good. Doesn't mean the tuning is still not good enough. So we have to make sure it's tuned properly for both the servo changes and for both the regulatory changes before we can say that the tuning is good enough for us to use. Whether this controller, whether advanced controller, any method for controller that we're going to use before, later, we've used before and we use it now, later, we have to take this into consideration to make sure that this controller that we have can work properly under set point change and the disturbance. We cannot be changing for set point, we have a different set of tuning. For disturbance, we have different set. We'll never get a good, what you call, optimum controller. But we have to be sure that when we use for set point change, and when this same tuning is being used for disturbance, it is going to be good enough to give us the result. As a reject the disturbance or give the set point that we want. Okay, that's same as before. We study again more so in the advanced where we'll dealing with a non-linear system or more difficult systems, slow systems. Not in this one, and also in the later we'll see the modern control strategies. This is more so important to be checking that we have to be able to control on both sides. Okay, so that is the